Okay, we're going to do a couple things in this video. We'll talk about monolinear. We'll talk about multilinear, and we'll talk about breaklines. So the basic consequence, and this is all with respect to the plated algorithm, right? So as an example of that, let's consider a 2x3 grid. So looks like this, right? Now that was monolinear because it only involves one curve, linear representing line. This is a curve, but all the same we're going to refer to as one line, one tracing. So this was 2x3. Now let's do a 2x4, and then we'll talk about some conditions on these things. All right, so there's a 2x4. The first number always referring to the rows. So if I do the same thing, notice that it's not monolinear. I haven't finished encompassing all the dots, but I have returned back to where I started. So let me grab another color, and if I then complete the process of encompassing the dots, I have two curves, right? This might be number 2, this is number 1. Two components, two curves. So we would call this, say, multilinear, or there are two components. And so what's the deal? Well, it has to do with the greatest common divisor of the grid dimensions. So a grid has two numbers, and it's the relationship between these two numbers that determines if it's monolinear. The greatest common divisor of 2 and 3 is 1. That's the biggest number that goes in both of them. The biggest number that goes in 2 and 4 is 2. It's two components. So we could test this idea. You know, if I did a 3x3, which we've seen several times, the biggest number that goes into 3 and 3 is 3. You know, so there's one component. There is another component. Now I would need another color here. Let me grab one, and then a third. So there are 3 components. So this is also multilinear. It has 3 components, or 3 curves. Now, the idea of breaklines is that we can increase or reduce the number of curves. So the example I usually use is this 3x3. Suppose I were to look at another 3x3 grid of dots, but I'm going to place a breakline right here. And what that's going to cause is, as you're moving around this brown curve, you can't get back to where you started. The breakline reflects you onto another path, and then you're back to where you started. Let's see how that works out. So I'll use the same color. I'm doing brown, and then I'm not allowed to return back to my start. The breakline stops me. So I reflect, and now I'm on this purple curve, and now I'm back to the brown. So that breakline had the result of joining two curves together. I still need this green one to complete enclosing all the dots. But now I have a new Lusona, and this is it's still multilinear. Now it has 2 components because of the breakline. Now you can add more than one breakline, and following this idea, what if I put one, right in here? That would join the green and the brown curves. So let's see an example of that. So I'm going to put a break line right here and a break line right here. And let's see, how do I want to, let's do it like this. I want to show you how the curves join. All right. Oops. So before, I would have crossed through that, but now I can't. So I'm effectively on the green path. And at this point, I'm back to the break line, back to this intersection, and I'm bounced off the break line, off the other break line. And now we have a Lusona that is monolinear. So this is monolinear. So, so do break lines always reduce the number of components? Well, let's look at some other examples. So here's a 2x3. Suppose I put a break line right there. What happens? Well, I can go around. Oh, I haven't finished, but now I need two components. So this was monolinear, is now multilinear. Two components, two pieces. So break lines can increase or decrease. Here, I was cutting something that's already monolinear, and I was also cutting it. Well, here, let's do a similar example. Look at this 2x4. Think intuitively, what would happen if I cut right here? You may not be able to see it, but this is the green curve. So if I cut that green curve right there, think about what's going to happen. Try to make a prediction while I do it down here. 2x4. Put a break line right there. So here I'm trying to do this green curve, but there's a break line in the way. So it cuts it into two pieces. The purple or violet piece remains the same. That doesn't pass through the break line. But this break line took us from 2 to 3 components. So break lines can increase or decrease. Now, as a good rule of thumb, if you take two different components and you cut them, you will join them. And it doesn't have to be right here. Consider this location. There's a green curve and a purple curve. So what would happen? Go down here. What would happen if I placed a break line, right there? Well, let's see. Okay, so let's see the result of this particular break line. So you still have this curve, but the break line didn't affect that curve anyway. Let's look at the green and purple break lines. So here's the green one. It can't continue through the break line, though. It's reflected twice. And then we see we've joined together these two separate components. So again, we went from 3 to 2. So using break lines, there's no unique way to reduce or increase the number of curves. A little experimenting may be required. There are usually several solutions that lead to the same result, though you may have differing levels of symmetry. Notice that in this example, where there's only two components in one break line, it's not symmetric, whereas in this one, it has a certain symmetry, up-down symmetry to it. All right, so I hope this was helpful. I'll stop right there.